Okay, hey there everybody. So welcome back. In this video, we're going to be learning just about a couple things, but those things are important. First, we'll be learning about the classical assumptions, so-called classical assumptions of econometric analysis. And then secondly, we'll be learning about the sampling distribution of estimated betas, or the estimated coefficients of our regression equation. Okay, and again, these are very important. Both of these are very important and central to doing econometric analysis. So over here, we see those classical assumptions. I'm just going to read through them quickly. I encourage you to pause and write these down. We'll go through each of them in turn, of course. But we assume that the regression model is linear, is correctly specified, and has an additive error term. Okay, we've talked about that in previous videos, so you should have some idea of what that's talking about. If you're not familiar with error terms, specification of regressions, please go back and look at the first 3 videos in this series. Okay, we assume that the error term is a zero population mean. Okay, we'll talk about that, what that means in a little bit. We're going to assume that all explanatory variables are uncorrelated with the error term. So the error term that we've specified, not correlated with our various independent variables, or X variables as we've laid them out before. Our observations of the error term are uncorrelated with each other, right? So the error term, so we've got a bunch of observations, error term, right, that those are not correlated with each other. The error term has a constant variance. No explanatory variable is a perfect function of any other explanatory variable, so our various independent variables, right, they can't be a perfect function of one or the other. So for example, if we had one explanatory measure was like distance in feet, and then the other explanatory variable was like distance in yards, and of course they would be perfect functions of the other, right? Feet would be just 3x of the other one, 3 feet to a yard, right? So that's not going to work, right? That's going to violate one of our assumptions. And finally, the error term is normally distributed. Now that's implied in several other of our classical assumptions. So let's go through each of these in turn. The regression model of linear is correctly specified and has an additive error term. Okay, we see that sort of structure right over here, right there. Okay, so we've got, in this case, a single explanatory variable, x I, and a single estimated beta value associated with that, beta 1, as well as an intercept term, beta 0, and then, of course, the error term. Now, this doesn't mean that the relationship between the independent variables and the dependent variables always has to be specifically linear, just that the model is linear. Okay, so for example, oftentimes we will find, or we will hypothesize relationships of our independent variables to our dependent variables that maybe look something like this. Okay, and so what we have here is the letter E is standing in for the base of the natural log. Okay, so what we have here is the idea that these are exponential relationships. So the relationship between our independent variable x1 and our dependent variable yi is not a strictly linear relationship. That is, as x1 increases geometrically, y is increasing arithmetically, which we can think of a lot of economic relationships where that's likely the case. And so when we design our hypothesized regression relationship, right, we need to incorporate those types of relationships into the model. Okay, so now how we do that is we transform those relationships into a linear relationship, which is what we see down here, where ln is the natural log. So in this case, what we have is the natural log of our dependent variable y is equal to beta 0. Well, you see the regular linear form here, again, where ln is natural log, so natural log of the x independent variable as well. Now, there are a variety of ways to do this, which we will be discussing in future units. Suffice it to say that our first assumption does not require that all these relationships between our independent variables, even relationships between independent variables, are not necessarily linear, and our relationship between our independent variables not necessarily linear, but that the form of the regression model is linear. Okay, those are two different things. Second of all, we assume that the error term is a zero population mean. In other words, we assume that the distribution of the observations of the residuals, right, looks something like this, okay, where it is its mean value is 0 and that it's normally distributed, okay. Again, just I want to make sure people, this is a problem that some of you are having, or difficulty some people are having. Error term, theoretical concept, residuals, observations, okay? Moving on then. All explanatory variables are uncorrelated with the error term, right? So we've got a bunch of things we're saying explains the movement in y, right? Like in our early chapters we said, okay, we're going to say that height explains weight, okay? And of course then we had we had an error term that we introduced, right? And we observed residuals in that. Well, we're assuming that the explanatory variable itself, okay, is not correlated with those errors, all right? So if one or more of the explanatory variables are correlated with the error term, then the estimated value of beta will not reflect the true value of beta. So we'll have a biased estimator if that's the case, right? So that error term is going to pull our estimate of beta in one direction or another. Okay, and this can happen. In fact, it's more common than not, right? It happens when one or more important explanatory variables is missing from our hypothesized equation. Okay, so something to look for, right? When we run, we'll be doing this shortly. Next time I do a little video of running regressions, right? We'll take a look at the residuals and see whether they meet these assumptions, because it's going to give us some simple indicators as to whether our estimated coefficients are sound or not. So observations of the error term are uncorrelated with each other. So if we plot those residuals, okay, what we shouldn't see is anything that looks like observations of the error term or the residuals are correlated with each other. So looking over here, right, in this case there would seem to be a clear functional relationship between observations of the error term, right? So we've got this kind of curvy, snaky line, right? And it looks like certainly these are not random, right? There's some kind of relationship here that's defining this kind of sine wave style relationship between observations. And this is certainly a violation of our assumptions, and therefore our estimated regression relationship is going to have errors. Okay. Also, we're assuming that our error term has constant variance. Now, with the term variance here, we mean, just like you would in your introductory stats class, same idea, right? So in fact, all those we'll stick with regular stats terms throughout the course. This problem is known in econometrics as heteroscedasticity. Okay, it's a big long word. Heteroscedasticity. Okay, right. And sort of here we have an illustration of that, right? So we can see that the variance of this error term is clearly increasing as we move off to the right, right? So it starts off very tight and then becomes quite broad. And this is also a violation that's going to result in biased estimators and an unsound estimated regression equation. We're also going to assume that no explanatory variable is a perfect function of any other explanatory variable. Okay. This problem is known as perfect multicollinearity, and I gave a brief example of it in the introduction to this video. If one of our variables is, say, meters, right, and then another one of our variables is centimeters, both of a distance, right? Those two variables are going to be perfectly correlated, right? So the meter relationship is just going to be the centimeter relationship divided by 100, right? So it's a perfect function of the other variable, okay? The second variable, whichever one we want to call a second, it doesn't really matter, does zero additional explaining and can't be, in this case, and can't be separated from the other one. So variations in the centimeter observations cannot be separated from observations of the meter variable. Okay. So examples of this type of problem, right? Wealth and income, right? Usually when people's income goes up, their wealth goes up, and when their wealth goes up, their income goes up. So it's difficult to separate those two concepts as independent variables. Now, in the case of wealth and income, they're not likely to be perfectly multicollinear, right? They don't move exactly together. Okay, they're going to be somewhat multicollinear, right? And indeed, in most cases, you're going to find a degree of multicollinearity between your independent variables, and so it's not that multicollinearity is a killer, just on the surface, right? It's really a matter of degrees. Perfect multicollinearity, however, is a violation and is going to result in incorrect estimated regression results. Okay, imperfect multicollinearity is something that we'll deal with, and I'll show you how to, if not remedy, at least identify and mitigate in future lectures. So having gone through those classical assumptions, then let's move over to the nature of the sampling distribution of our beta hat, or our estimated beta coefficient. So you'll recall that our estimated regression equation contains estimates of beta, right? So we need to consider the nature of the x values associated with the estimation of beta, right? So we think about those observations, those independent variables. What do those observations look like relative to our estimated value of beta? Okay. And what is that estimated value of beta? What is the relationship of that to the true value of beta? Okay, so to think about that, somebody like, I don't know what he's talking about. Okay, you will in a second, right? Okay, so consider our regression from an earlier equation, right? So this is our weight height thing that we did in chapter 1 and chapter 2. Okay, what if we were looking at, we just sampled the heights of some track runners and some sumo wrestlers. Okay, if you don't know what a sumo wrestler is or a track runner, look it up now. Okay, right? Okay, so what would the distribution of our sample look like? What would the estimated beta be representative of the relationship between height and weight? Okay, so if we took those sumo wrestlers and we took those track runners, right, we might get something that looks like this. That is our relationship between heights and weights. We've got our sort of track runners over here, and we've got our sumo wrestlers over here. And we've got sort of a normal track runner, and we've got a sort of normal sumo wrestler. But they're different, right? The mean of that entire relationship is not representative of the population, okay, that we've sampled. If we were to take the mode relationship of that sample, okay, we might find that it's this bimodal. We've got sort of one group over here, one group over there. Okay, and when we combine the groups, the distribution of our observations is no longer normal. It's no longer sort of bell-shaped. It has this sort of two-hump, camel type thing. Okay, and if that ends up being the case, right, if we don't have this normal distribution of observations of our independent variable, then our estimated value of beta is going to be biased, right? Similar if we have sort of a long tail set of observations, right? We're going to introduce some bias into our estimators. It doesn't matter which way the tail goes, either way, okay? If we have some weird outliers, so we've got a little hump at the end of a tail, it's going to bias our estimators, right? We are assuming when we do this that our sample observations of our independent variables are normally distributed. Now you might be saying, well, geez, it just isn't going to be so sometimes. Okay, that's right, it's not. And when that's the case, then we need to think about how we're going to change this situation in such a way that it normalizes these. So in this example, right, we may separate out. We may create a separate variable for sumo wrestlers and a separate variable for our track runners. Right? If we separate those out, then we perhaps normalize that distribution. But that's something we need to do, right? We can't just leave it be where we've got these bad sampling problems. Okay, so we say an estimator is unbiased when this condition holds. That is, when the expected value of beta hat, okay, or the expected value of our estimated value of beta is equal to the true value of beta. So the true value of beta. Okay. So moving beyond that, right, we would also prefer, okay, that the variance associated with the estimated value of beta is minimized. So, you know, oftentimes we can do this through increased sampling, right? So we get more and more samples, more and more observations, right? What often happens, right, is that sort of the observations sort of pack around this mean much more tightly. So there's more sort of normal, and less deviations from sort of normal, where normal is the mean value. So if we're, you know, noticing wide variations around beta, right, it might be signaling to us that we really need a bigger sample size, or that we really need to think about how we're doing our sampling. Now, oftentimes that's simply not possible, right? The sample or even the population is what it is, and it may not be sufficient to produce, you know, really nice, tightly packed, low variance estimate values of beta. In these cases, you know, what we have is we simply have to be more modest with our estimated results. Okay, but we have to be aware of that, and we should certainly be aware of the desirability of low variance associated with estimated beta values. Okay, that's it for this time. It was a short and tidy one. I hope you've all learned some things. Again, these are important to keep in mind, and sort of keeping all these classical assumptions in the sort of back of your head every time you run a regression, and then running appropriate tests, right? So like things like basically plotting the residuals, plotting the observations of your independent variables, and just taking a look at it, right? Of course, you could create graphical relationships of those observations as well, if you sort of don't see it right away. But those are sort of good, you know, getting started style tests to really try to figure out, you know, how good your regression results really are, or how making sure that your estimated coefficients are not unbiased. And if they are biased, you will be able to get a good idea about how to start remedying those problems. All right, we'll leave it there. Thanks, everybody. See you next time. Take care. Bye.